One of the chief reasons Pluto got demoted to the status of a dwarf planet was its strange orbit. Pluto takes 248 years to complete one revolution around the Sun. Since its discovery in 1930, the celestial body hasn't even completed a single orbit. But that's not the only peculiar thing about it. The nature of Pluto's orbit is an ongoing mystery, something that astronomers became aware of shortly after its discovery. The orbits of all the 8 planets in the solar system are nearly circular and lie close to the plane of the Sun's equator. The plane of Earth's orbit around the Sun is called the ecliptic, and almost all the planets have orbits with only slight inclinations to the ecliptic, which makes it convenient to treat the ecliptic as the fundamental plane of the solar system. But things are different in Pluto's case. It has a highly elliptical orbit inclined at 17th to the ecliptic, way higher than the orbital inclination of all the planets in the solar system. Pluto's orbit intersects with Neptune's orbit, and because of that, the tiny world lies closer to the Sun for almost 20 years in each orbit. Now the intriguing question is that why hasn't it collided with Neptune? What has kept Pluto stable in this weird orbit for billions of years? And most importantly, what roles do the planets of the solar system play in trapping Pluto in its odd orbit? Astronomers have long wondered why Pluto doesn't collide with Neptune, and the answer lies into terms of celestial mechanics, azimuthal libration and latitude libration. Because of these two phenomena, Pluto can safely orbit the Sun without colliding with Neptune. Understanding these two terms is easy. Azimuthal libration describes that whenever Pluto crosses Neptune's orbit, it is always at least 90 degrees away from Neptune. On the other hand, latitude libration ensures that, when Pluto reaches its closest point to Neptune or any other giant planets, it always stays high above them and the solar system plane. This behavior of Pluto's orbit is known as VZLK oscillation, referring to von Zeipel, Lidov, and Kazai, who studied this phenomenon as part of the famous three-body problem. This problem considers the initial positions and velocities of 3 massive objects. These parameters are used to solve their equation of motion following Newton's 3 laws and the theory of universal gravitation. Both these factors are together held responsible for keeping Pluto out of danger. However, in the late 1980s, numerical simulations revealed that despite these two prevailing properties, Pluto's orbit is technically chaotic. Some minor deviations of initial conditions led to exponential divergence of the orbital solutions over tens of millions of years. But fortunately, the two unique properties of Pluto's orbit persist over gigayear timescales, thereby making its orbit remarkably stable by limiting the chaos and not allowing them to take over the stability. To better understand the phenomenon involved in keeping Pluto's orbit stable, the researchers simulated the orbital evolution of Pluto for up to 5 billion years by using 8 combinations of giant planets' perturbations. So basically, they wanted to know how the gravity of different planets affects Pluto in various combinations. Researchers ran simulations combining different cases. One of the simulations only involved the influence of Neptune, while 3 combinations considered the impact of gas giants in pairs. These pairs included Uranus and Neptune, Saturn and Neptune, followed by Jupiter and Neptune. Besides that, 3 combinations included 3 gas giants together: Saturn, Uranus, Neptune, Jupiter, Uranus, Neptune, Jupiter, Saturn, and Neptune. And in one of the combinations, the team also considered all the 4 giant planets at once. Finally, after analyzing all results of the simulations in different combinations, here's what they discovered. Neptune and Pluto are long known to exist in a 3-to-2 orbital resonance. This means that Pluto finishes 2 of its orbits for every 3 orbits that Neptune completes around the Sun. Orbital resonances can significantly enhance the mutual gravitational influence of the bodies on each other and are very common in the solar system. One of the famous examples is the 1-2-2-2 for resonance off Jupiter's moons Ganymede, Europa, and Io. The simulations revealed that Neptune significantly ends Pluto's azimuthal libration due to orbital resonance between Neptune and Pluto. However, as far as Pluto's latitude libration is concerned, Neptune doesn't contribute much. The situation becomes tricky in the case of the next closest giant. Uranus' gravity destabilizes both the azimuthal and latitudinal constraints, thereby favoring the destabilization of Pluto's orbit. This means that if Pluto's orbit were only governed by Neptune's and Uranus' gravity, it would have become unstable after tens or hundreds of millions of years, and such a scenario would have caused Pluto to collide with Neptune. or fling entirely out of the solar system. So how is Pluto still having a stable orbit? What's saving it from the chaotic orbital mess? The answer lies in Jupiter's gravitational power and a little bit of Saturn's gravitational pull. Jupiter and Saturn lie far from Pluto compared to Uranus and Neptune. However, their gravity is still strong enough to dominate the Plutonian system. Hence, they become core contributors to keeping Pluto's orbit stable. As the current simulations have revealed, even Jupiter's solo gravitational influence is enough to keep Pluto's orbit stable for at least 5 billion years. These results are likely to have significant implications for studying the dynamics of the solar system in a more detailed manner. Following these simulations, one can also trace evidence for the existence of planets that were probably once a part of the system but got ejected from the solar system billions of years ago. The results can also explain the origins of Pluto's orbit, along with those of other bodies with high orbital inclinations, including the trans-Neptunian objects that are not well studied yet. The new research shows that Pluto stays safely in its unusual orbit thanks to two key mechanisms: azimuthal libration and latitude libration, which prevent it from ever colliding with Neptune. Advanced simulations reveal that while Neptune's resonance shapes Pluto's orbit, it's actually Jupiter's powerful gravity, along with Saturn's, that stabilizes Pluto over billions of years. These findings help scientists better understand the solar system's long-term dynamics and the possible history of planets that may have been ejected long ago. Make sure to like it and subscribe to our channel for more